Hello, my name is Scott Francis, Senior Solutions Architect at Amazon Web Services, and today I'll be talking about the advanced in-vehicle cloud service applications that the AWS Connected Mobility Solution enables, and I'll show you a short demo using the NXP S32G processor. As the number of devices and computing powers in vehicles grows, the interconnection of how those services changes, starting with convenience. Drivers seek to automate what was previously manual. Service reminders, automatic windows, fairly modest and computation and limited interconnection of services. With more capabilities, personalization becomes possible. Media portability for time and place, shifting between vehicles and locations. As the possibilities grow, access and enablement of services becomes responsive with new interactions. All this tech comes together to create new things and increasing the pace and impact of innovation. When we talk about connected mobility, it really means many different things to different audiences. OEMs want to reduce their warranty costs, provide new end user personalizations. Service providers want to deploy new and innovative services. And commercial fleets seek to maximize the uptime and the operational efficiency out of every asset in their inventory. The evolution of electrical architectures that started 10 years ago has delivered benefits, starting with entertainment services that are primarily local in interaction, but are served from the cloud. Next, drivers have gained benefits from applications to be more effective or productive with their time in the vehicle, starting with mapping and navigation and moving to the automation of routine tasks like parking and charging. Some of the next generation of services include opportunities for commerce, not just shopping and delivery, but new businesses like usage-based insurance or even tires as a service. The vehicle is becoming part of an ecosystem of services. Software and connected mobility solutions are an absolute must for every industry player, whether internally created or with partners. The customer's obsession is now all around the services, not the physical vehicle. People make decisions around whether a vehicle can get updates and the service itself and what the UI is. The vehicle manufacturer is now really competing to add value around connectivity. If you don't control the connection and the services, you don't control your future. There's no longer any question that the vehicle is part of a broader ecosystem of connected services. We see four major business challenges. One, to innovate mobility services that create new revenue streams requiring integration from vehicle to cloud and to an app. Two, those experiences must be personalized and continually updated to delight the customers. Those users want customization and an awareness that will travel with them from one vehicle to the next. Global fleets are looking for that higher operational efficiency and for competitive advantage. The very notion of vehicle ownership is becoming more of shared ownership and shared utilization across those fleets. OEMs must democratize their internal access to fleet data to accelerate innovation. We've designed the solution called the AWS Connected Mobility Solution to meet these challenges. Let me walk you through it a little bit. On the left, you see what happens in the vehicle. Amazon provides a set of IoT edge compute building blocks, including the IoT SDK, Greengrass software that works with edge devices. And this provides Lambda serverless functions for over-the updates, security, ML at the edge, and other local logic that can be customized. With the latest update to CMS, we also provide the connected device framework for lifecycle fleet management of IoT devices, including initial activation, certificate management, rotation, and business policies for all of those. In the middle of all this is the business logic, and this is where the vehicle data is stored and processed into different applications and services. Finally, on the right are the APIs and communications capabilities that support the applications and business intelligence. All this runs serverless, highly scalable, no infrastructure to manage or patch, and is purely pay as you go. This connected mobility solution is born in the cloud using microservices and serverless with managed services. It's secure and open source. In the next few weeks, we will be announcing this for publication and will be made available on GitHub. Let's drill down into some of these areas. First, the right building blocks to help you create connected vehicles and deliver those mobility solutions. One of the core systems is IoT Greengrass, used to run inference at the edge. And Greengrass is cloud managed, even though it's running in vehicle. Those inferences can include anomaly detection, which can run in vehicle or can run in the cloud. It can be tuned for the specific hardware in hand, such as the S32G that we're going to be highlighting later. The data is then ingested into our serverless IoT core, where the insights can be made across a fleet of vehicles and business opportunities created based on location or condition monitoring. Second, that CMS can empower some of these new in-vehicle experiences. Let's focus on the in-vehicle component where IoT Greengrass forms the core service to maintain machine learning models, manage OTA updates, and run inference locally from those models. The Lambda functions, which execute locally under the management of Greengrass Core, are customizable and expandable for controlling local logic, compressing data, and sending different bits of information as needed to other different subsystems or up to the cloud. These functions are all managed by the AWS IoT Core services to ensure the right versions are always up to date. What we're doing is bringing the cloud and all of its modern tools right down to the edge. But what is the edge? How do we define that? Edge workloads are fundamentally driven by three different types of laws. They're limited by laws of physics. The data can't move anywhere fast enough and come back fast enough, such as something that is sub-millisecond response times. Laws of economics. We're backhauling all the payload that's involved with every sensor just to create a historical picture or overall fleet history of loss and baselining of different parameters might be ineffective to do over high cost bandwidth. Or a law of the land, where it's desired for that data to remain sovereign to the location where it originates or be processed locally. Some of the other workloads on there look more like traditional IT, where there might be hybrid, there might be mid-tier, or it may just be the way we've always done things. For us, this is the edge. We take all those things from the cloud and push them down to executing, in this case, in vehicle. And this notion supports different types of emerging architectures, whether that's a domain vehicle architecture or a zonal vehicle architecture. CMS architecture is flexible to both of these approaches, and the NXP S32G processor can provide the key gateway and domain controllers for both situations. I've mentioned a few times about using AI and inference and ML at the edge. And what we see for that is it's really part of an AI ML lifecycle or ML ops. And this is where data scientists using AWS services can work with their preferred tool sets, libraries, functions, networks, and so on large volumes of data, but distribute these actions and create the inference and the outcomes right on the edge. We can then backhaul these actions and these inferences into the cloud to complete the cycle of learning, continuously monitoring and refining how well the inference and machine learning function is operating. We built all this using Amazon SageMaker, and we built SageMaker from the ground up to provide every developer and data scientist with the ability to build, train, and deploy ML models quickly and at lower cost by providing the tools required for every step of the ML development lifecycle in one integrated, fully managed service. In fact, we've launched over 50 plus capabilities in the last year alone, aimed at making this process easier for our customers. In 2019, we launched Amazon SageMaker Studio to bring all this together into a single pane of glass so that you get access to all your tools in one place. And now, SageMaker Edge Manager provides the ability to extend that ML ops cycle to edge deployed models with updates, continuous OTAing, and keeping those models fresh, and monitoring their performance so that if data drifts, if inference performance drifts, those models can be refreshed, retrained, and re-updated on the edge. But deploying the models at the edge can be hard. In the cloud, you often have, or might think you would have, bigger and better models, whereas on the edge, you'll have limited resources. You typically have many device platforms to contend with, whereas in the cloud, you have more capable and more scalable, more predictable devices. It's unlike services in the cloud. This limited compute and connectivity can take months of hand tuning of each model to optimize its performance and fit within the specific hardware constraints. For that, we have SageMaker Neo to do that optimization and targeting for the particular hardware. In addition, many ML applications require multiple models to run on a single device. A self-navigating robot needs both object detection to detect obstacles, classifier to recognize obstacles, and a tree-based model to determine action. Once a model is deployed in production, model quality can decay because real-world data used to make prediction often differs from the data used to train the model, which can lead to inaccuracies. So all of this together has come into SageMaker Edge Manager, which is our model management for edge devices. With SageMaker Edge Manager, which includes SageMaker Neo as a compiler, we can improve performance of those models up to 25 times, integrate with a wide variety of devices on the edge, continuous monitoring of the performance of those models, and run multiple models on each device. The workflow consists of a series of tools and services that easily take ML models, prepare and optimize them for edge inference, and then manage so that inference as part of an overall ML ops cycle. Let's take a look at SageMaker Neo. SageMaker Neo allows you to train and then run on a multiplicity of device hardware with double performance, no loss in accuracy, and oftentimes 1/100th the compression of the original model size. This is a quantization and an optimization function, and it's all integrated with SageMaker. This also references Model Monitor, which is part of the SageMaker Edge Manager dashboard to keep track of model versions and their performance. The data comes in and out of S3 and is used for monitoring, labeling, and retraining. In the cloud, you can gauge the health of the model fleets, not just of a single device, but the entire fleet of all the deployed inference engines that are in all the vehicles from a single SageMaker Edge Manager dashboard. You can then use the model monitor for drift detection and detect this accuracy shift, identify the specific devices, and isolate the specific data causing that decay. You can then use SageMaker Ground Truth to relabel the data, retrain the model, and deploy it to the edge. Going back to CMS, CMS also helps you organize that data to drive operational efficiency and that innovation that fleet managers are looking for, providing a full view of the data in the fleet, allowing large-scale insights that can drive product innovation, product improvements, efficiencies through better visibility into exceptions and models for cost, and API services to expand all of these and democratize access to that data. It's this exception management that is particularly powerful within CMS. CMS also provides, through the CDF or Connected Device Framework subcomponent, an ability to securely update vehicle software over the air. This can be Greengrass itself. Greengrass itself is managed this way on the edge, as well as the ML models I was discussing earlier, but could be any component, could be any binary object that you care to deliver and update from version to version can be securely updated through an OTA mechanism. And the fleet management is given a configuration engine as well, which allows you to specify characteristics by geography, software, dice and slice the fleet, look at it in different views in different ways. Visibility across all the vehicles of a particular type, vehicles within a geography, or just look at certain versions of software so that you can create, say, a blue-green OTA deployment strategy or a canary detector to impanel certain versions, perhaps in a test fleet, to look and evaluate whether inferences or new software versions are delivering the intended benefits. CMS provides a number of flexible entry points and is not a single monolithic solution. You can mix and match these and combine them to deliver the right sort of solution that is right for your customers or your application. We provide a number of different things, including ML analytics, anomaly detection, which can run cloud side or edge side, cloud storage to archive and build a data lake that can be small or quite large, ingest to the cloud at volume, at the speed at which the data is being created, and of course that edge inference. CMS provides provisioning and lifecycle management through the connected device framework. And the most critical aspect here is to deploy and manage the lifecycle certificates and software for those over-the-air updates, as well as securing the communications between the vehicles and the cloud. This framework helps you model and organize the devices through business logic for that lifecycle management, including certificate rotation, validation upon exception, placement of components, both in service as well as part of original commissioning of a vehicle. Connected mobility solution also includes a vehicle simulator framework. There's a rudimentary simulator that's part of it that simulates the telemetry that commonly comes off an internal combustion engine car, but can be customized to provide any type of modeling or any type of data that you can think of, so that you can spin up these synthetic containerized vehicles in the cloud, hundreds or thousands of them as needed to help drive your simulation or drive your modeling. This allows you to create modeling with real telemetry values and replay them either from captured systems through augmented systems where you take real telemetry and salt it or spice it up or adjust it, randomize it around those values, or use pure simulation. And you can mix and match all of these approaches. This can be used to load test the system and validate different types of usability and usages before you ship it. The fleet monitor is the user interface, and that's the reference design that customers can customize for their own use or build a whole fresh one. Amazon is not a fleet management company per se. We just provide that fleet manager as a reference design for customers to customize, as well as a way to demonstrate how to use the APIs and the data. Together with NXP, we built an EV management system demonstration using the NXP S32G processor and CMS. And this is one example of how that system was customized. Let's take a closer look at how that demo was put together. The S32G is a highly capable, high-performance processor, and it's encapsulated in an architectural component called the NXP Gold Box. And that consolidates and aggregates signals from vehicle domains and components, and can not only act as the communications gateway, thus separating that concern from the other components, but can also act on those signals, providing advanced functionality, such as might be triggered from ML models or regular old business logic. Inside the vehicle, the Gold Box acts as that gateway, collecting data from the Blue Box, which is the autonomous ADAS component, other legacy ECUs or less capable ECUs, and the new Green Box EV management system. All that data is passed to the AWS IoT Core, where we are running SageMaker to both develop models and then SageMaker Neo to compile those and deliver those back down for inference on the Gold Box. The way that works is Gold Box is running IoT Greengrass Core, identified with a core device certificate and a hardware secure element to store that data to ensure that communications to the cloud are secure and encrypted. The message is sent to IoT Core and then back to other local devices. In the next slide, what I'd like to do is have Kurt Hillier from NXP demonstrate the system in action.
Hello, I'm Kurt Hillier, Technical Director at NXP. Today I'm introducing to you for the first time the NXP and AWS Connected EV Management System. The Connected EV Management Solution demo incorporates three major components: the Green Box 2 serving as a Powertrain domain controller, the NXP Gold Box acting as a service-oriented gateway running AWS IoT Greengrass Core, and then the AWS Cloud Connected Mobility Solution. These encompass the major features of the demo. The demo incorporates three major use cases for connected vehicle: predictive maintenance, advanced vehicle diagnostics, telematics, and fleet management. The demo showcases three key connected vehicle use cases. It unlocks the value of real-time vehicle data to provide many benefits. Finally, it establishes the foundation to extend these use cases for vehicle-wide support. So each one of these pieces has a very important function. The powertrain control is all about moving the vehicle and moving it efficiently, safely, and securely. The S32G Gold Box does secure connectivity within the vehicle domain, so connects ADAS, powertrain, autonomous drive, body, chassis, lighting, anything that you need to have securely connected inside the vehicle, you can run it through the gateway to do that type of connectivity. And then finally what we do is we connect securely to the cloud. And that's where we see the Amazon Web Services connected mobility solutions to bring these types of use cases that we've discussed to life. The NXP Greenbox 2 electrification development platform implements a Powertrain domain controller. This type of functionality can support both hard real-time embedded control for things such as electric motors, battery management systems, as well as supervisory functions such as functional safety, energy management, range extension, and all of those are brought together into the Greenbox development system. The dual electric motor control is something that NXP has been developing for a number of years. The field-oriented control algorithm runs on top of the automotive math and motor control library. This library is optimized to execute quickly on the ARM R52 cores inside the S32S in Greenbox 2. For the battery management system, NXP makes an MC33772 cell monitor. These precise multi-cell monitors are able to detect and do cell balancing and battery measurements with a high degree of precision. So that's the second application. The third application implements an MQTT interface to an IP stack, an Ethernet IP stack, that is allowing us to communicate to the S32G that's running the AWS Greengrass core. In this way, we can take the vehicle analytics, pass those to the S32G for edge processing, and then further offload those to the cloud for cloud processing. The final algorithm that runs on a slower loop but is very important is the energy management system. This system looks at all the driver inputs, the vehicle characteristics, and the known torque sources in the vehicle, electric motors, combustion plants, and determines how do I most efficiently use my energy to maximize my range. All four of those applications run inside Greenbox in the Powertrain domain control proof of concept. Now let's see the demo in operation. As you can see here on the demo track, we've got the Simulink model with the vehicle animated and then the vehicle metrics off on the right side here. As we drive the vehicle, you'll notice that the electric motors are now spinning and they correlate with the vehicle speed. And then a little further down in one of the bottom charts, you can see that we have a torque vectoring algorithm that runs. So you can actually control the amount of torque that you apply to the left and the right motor to assist with steering. And then we'll get out to the straightaway. Now that we have the vehicle on the straightaway of the M-City test track, let's take a look at the Amazon Web Services cloud. So this is the fleet management software in the CMS system, the Connected Mobility Solution. We'll click on our car. You can see our 2021 car here, and you see the dot on the map. This is where we are on the M-City map. You see we've got the software version, trouble codes, an odometer reading, battery charge, the current speed, and a remaining useful life of one of the components in the vehicle. So as we start driving, again, our tires are going to move and we'll start moving down the test track. And then we can see that our GPS dot and our location of this vehicle in our fleet is actually updating as well. One of the algorithms that runs behind the RUL, the remaining useful life, is a SageMaker LSTM neural network. So there is a set of data that we feed to that machine learning algorithm, and it's doing a prediction on the remaining useful life of the engine. For more information about Greenbox 2, Goldbox, and our connectivity services with AWS, please visit nxp.com.
So how do you get started with CMS? So as I mentioned, we'll be releasing in a few weeks, and the link for learning more about CMS is off of aws.amazon.com. And you can start prototyping right now by getting in touch with your account representative and asking for access. As I mentioned, the source code is coming soon. And we have a number of partner solutions which can be added on to CMS solution, or you can develop use cases of your own. And I look forward to hearing more from you in the coming weeks as we release this to the public. And thank you very much for your time today.